Continuing with the used car example, this is problem 33. We're actually going to go ahead and find the regression line, plot it, use it to answer some questions about this linear model. And I want to find the equation of the regression line, which is the first thing they ask. And I want to find it two ways. Let's do it partly by hand. Let's use the calculator to find the key one variable statistics of the two different variables, the age and the price. And then we already have the R value, and we can plug those into the formulas. And then, of course, we can also let the calculator do it to check our work. So let's do stat calc 1-bar stats on age. And that'll give us our X bar and our SX. The X bar is 6. That's the mean age. And the SX, it's giving us as 3.708. Okay. We probably don't need that kind of accuracy in the end, but for intermediate calculations, we should always try to keep a little bit more. Okay, let's go stats, calc, 1-bar stats on, I'm going to do second list, and then go down, somewhere down here is price. Okay, so now we get the mean price, 6775.6, let's say. Okay. And the standard deviation of the price is 3624.4. Okay. And so that allows us to calculate the linear model. The slope, remember, was very nice. If you standardize it with z-scores, they talk about in the book how it's really beautiful if you always talk about z-scores, then the slope is exactly just a little r. But we want to go back to actual years and dollars, and it's not that hard to convert back. You multiply by the standard deviation of the price, SY, over the standard deviation of the age. Okay, so let's put that all in. We already had the S from the previous problem, minus 0.946. I'll just copy and paste that. Okay, times, let me copy and paste this because it'll look better. And I'm just going to plug this in, 3624.4 over 3.708. And we get minus 924.67. So what are the units on that? Remember, always want the units as dollars per year. It's always just the units of the top minus units of the bottom. The units of the variable you're trying to predict divided by the units of variable you're using to predict it. So this is going to say, this is part B actually says, explain the meaning of the slope of the line. Well, that means we can always say it in the same way. 1 unit more in X gives us this many units more in Y, less in Y because it's negative. So 1 extra year of age, we predict about 925 less dollars in advertised price. Now, does that mean it's guaranteed? Does that mean it's a perfectly linear relationship? No, but this is just the best guess according to this method of guessing. And it's a pretty good method of guessing. Okay. What about the intercept to actually get the whole equation of the line? This is the equation we want to get. B1, or M, you can call it either one, is the slope. We've got that. We want the intercept so we can actually just have the exact equation of the line, not just the slope. Well, they point out in the book that the one thing you do know you want the line to go through, aside from having the slope, it's supposed to go through the point, which is X bar, Y bar. So it should work if you substitute in X bar, the mean of the X's, and Y bar, the mean of the Y's, into here. And then you can solve for B naught. That's the mystery intercept. We're basically just saying we're using the point slope method of finding the equation of a line. We know the slope from this fairly sophisticated piece of mathematics that is in one of the math boxes in the chapter. And then we know that it should go through a certain point, the mean, comma, the mean of X and the mean of Y. And then we just solve. Okay, so that's something we can do. So the mean of Y was 775.6 minus, and then 924.67 times the mean of the X was 6. Okay, and we can calculate that, and it doesn't put it in the place I want it. 1227.6. Okay. Let's see. Oh, and so, okay, I made a nice error. Okay, I'm kind of glad I made this error. This doesn't make a whole lot of sense because B0, B naught, should be the price, the predicted price for an age 0 car. That's a really cheap brand. That would be a brand new car. Now, it would be weird to extrapolate from used car data to a brand new car, but still, this is way, way, way off. what happened here is I had a minus for the B1 and I forgot the minus here. So it's minus a minus there. So really this is a negative quantity. It's exactly the kind of error people make all the time. So that calculation was wrong. Okay, let's delete that and do it again. Aha, 12,324. Okay, so that would be our extrapolated price for a brand new car. Almost certainly not correct because new cars are just a different market from used cars. But, and see, it's really an extrapolation into an unreasonable regime for this model. But we can now write down our model that y hat, the predicted price, is 12,324 minus 924 let's just say 0.7. Actually, 924.7. Now that we're getting to the final kind of answer, let's just say 925. It's kind of ridiculous to do this to pennies. Times x. Okay. And that's our predicted linear model. Okay, let's see what other questions they ask us about this. Part B was already find the meaning of the slope of the line. And we already answered that. Part B, the slope says that for every additional year of age, we predict roughly a price drop of about $925. Okay. And part C, explaining the meaning of the intercept. Well, we talked about that. That's a pretty fictional price of a new car. The intercept is our known to be bad prediction of the price of a new car. But we don't really want to use that as a prediction, but it's kind of a fictional starting point. Okay, if you want to sell a 7-year-old Corolla, what price seems appropriate? Okay, so that's where this starts to really be useful, this explicit formula. We're just going to say, okay, what's the predicted one for 7? We're just going to plug in 7 for x here. Put a times there. Okay. And so it looks like 58.49. So this would be a really useful thing. If you say, okay, I want to price my 7-year-old Corolla at a reasonable price that people will probably be able to buy, but isn't too low. I could just kind of use this data and try to actually put it right on the regression line. Definitely doesn't mean that every 7-year-old Corolla you see maybe next week in the paper is going to have exactly this price. But this would not be a surprising price to see, and it would be a good one to price your own car at if you wanted to sell a car that was a 7-year-old Corolla. Okay, now it says you have a chance to buy one of 2 cars. They are about the same age and appear to be in equally good condition. Would you rather buy the one with a positive residual or a negative residual? So remember, the residual is always the actual value minus the predicted value, the y minus the y hat. Okay. And so would I rather that be positive or negative? Well, I want a cheap car. I want something that's kind of underpriced according to this model. So I'd like that to be negative, because that's when the y, the actual price, is less than what I would predict, what I would expect. Okay. I wouldn't want the one with a positive residual because that would seem overpriced. Okay. So such a car with a negative residual will seem underpriced, which is good as long as you're not suspicious of, well, maybe I didn't really look at the condition of the car very carefully. Okay, so the main thing here is to remember, if somebody starts talking about, oh, negative residual, if you don't remember which way this comparison is defined to be, what the definition of the residual is, that it's the real minus the prediction, then you're going to get completely backwards. So that is really an important thing to understand. Next part, you see a for sale sign on a 10-year-old Corolla stating the asking price is $1,500. What is the residual? Okay. Okay, so we have age x equals 10 and y equals 1,500. Okay, so the residual is the real minus y hat of 10. Okay, so that's 1,500 minus, put in parentheses, take this formula, I'm going to put a 10 in here. Okay, and I'll just calculate it. Okay, So it looks like, and not too surprising from what we've seen from the data, if you go back all the way to the data, 10-year-old car, somewhere in the 3,000s probably is what we'd expect. 1,500, that's cheap. That is $1,574 cheap. Okay. And so I don't know, I'd kind of wonder, half the price that you'd expect from the prediction? I mean, maybe it's a great deal, or maybe it's a crappy car. Okay. And would this regression model be useful in establishing a fair price for a 20-year-old car? Explain. Okay. Well, now that's where this linear model gets a little bit suspicious. Okay. If x equals 20, what would it predict? Okay, y hat of 20, let's just copy this down and change it to a 20. We're going to see something very suspicious when we put this in. Negative. Now, a 20-year-old car, a 20-year-old Toyota Corolla is somewhat rare, but you can get them to last that long fairly often. And you wouldn't have a negative price for that. So this model is not good for that, and the simple reason here is I'm extrapolating. I'm going way beyond the x values that were used to create the model, and that's never a good idea. There's another reason, though, I think that's a little bit suspicious, is we were using a linear model, and we could have already said a linear model could never possibly be right for a very large range of age values. Never right for a large range, because it would always have this problem. It would be a negative slope line, and that's always going to hit the x-axis and turn negative. So it might say that re-expressing the data, which we still are going to talk about, is a bit better. Remember, we had a pretty good reason to say that this was linear with the shape of this scatter plot. But if you take this down, 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 it's going to produce unreasonable results. Okay. Let me just show you real quick. I promised to do this on the calculator as well. We can look at stat calc, and we go down to 8. That does the linear regression and all the stuff we were doing by hand automatically. So real quick, we'll just do age, comma, price, and then we do another comma, and then we do vars over to y vars, enter, and enter for y1. That puts the formula, when we enter, the y equals a plus bx formula here, it puts that into the y1. Now notice, it's not exactly what we were getting. I'm not sure exactly what the subtle reason is that they're getting it off just by like a few, but it's very, very close to what we got. And when we then look at y equals, it's automatically put that formula, it's not just a number, it's actually the whole formula, you see the rest of it, in there, and then the regression line comes in. Okay. And so that is a nice way to confirm, okay, it looks pretty good. The next thing that we could do is we could plot the residuals. Why not do that? Since they tell us to always do it, they just didn't ask us to do it in this problem. What we can now do is go to stat plot, and I've actually got it set up already. It's a scatter plot, and I put in age, and if you look at the list of names, you'll see, I'll show you, resid for residual is here. And then we can graph it. The problem is it's going to not show up real well because you can't plot them on the same scale. So what we'll do is we'll go to y equals and turn off plot 1, turn on plot 2, and then do a zoom 9. And there's the plot of the residuals. Oh, and there's the y equals. We don't really need that right now. You can see there's not a lot of structure to the residuals, although I would say it maybe is high, low, high, which is suggesting that maybe there is a bend in the data, so maybe re-expressing it might be a good idea eventually. But it's not absolutely necessary because the linearity is pretty decent.